Okay, guys, recording in progress. As I mentioned before, my voice still not that good. The doctor, yesterday I've been to the hospital and the doctor asked me not to speak a lot till the medication. He said, may I take a week to 10 days to have my throat recovered after the infection that I had during the last 2 weeks in my lungs. So don't worry, it's not COVID, but it was an infection, a bacterial infection, but made me very tired. I recovered from the infection in the lungs, still that my throat need some treatment to be recovered. As I mentioned, after those classes, before the final exam, we'll have a class that will solve some question together using the handwritten board that I have to solve this question as a final exam preparation. Today we'll continue with as what we used before last week during to my health condition. So we'll continue with multiple feature linear regression, and then we'll go to some regularization concept, the overfitting concept. Then we'll start with clustering and some supervised machine learning classification algorithms. So I'll share my screen now and we will start. Which screen I use? Can you see my screen, guys? Okay, thank you, Gurpreet.
About to talk about a new version of linear regression that's more powerful, one that works with multiple variables or with multiple features. Here's what I mean. In the original version of linear regression that we developed, we had a single feature x, the size of the house, and we wanted to use that to predict y, the price of the house, and this was our form of our hypothesis. But now imagine what if we had not only the size of the house as a feature or as a variable with which to try to predict the price, but that we also knew the number of bedrooms, the number of houses, and the age of the home in years. It seems like this would give us a lot more information with which to predict the price. To introduce a little bit of notation, and we sort of started to talk about this earlier, I'm going to use the variables x subscript 1, x subscript 2, and so on to denote my, in this case, 4 features, and I'm going to continue to use y to denote the variable, the output variable price that we're trying to predict. Let's introduce a little bit more notation. Now that we have 4 features, I'm going to use lowercase n to denote the number of features. So in this example, we have n equals 4 because we have 1, 2, 3, 4 features. And n is different from our earlier notation where we were using m to denote the number of examples. So if you have 47 rows, m is the number of rows in this table or the number of training examples. So I'm also going to use x superscript I to denote the input features of the ith training example. As a concrete example, let's say x2 is going to be a vector of the features for my second training example. And so x2 here is going to be vector 6, 3, 2, 40, since those are my 4 features that I have to try to predict the price of the second house. So in this notation, the superscript, the superscript 2 here, that's an index into my training set, right? This is not x to the power of 2. Instead, this is, an index that says, look at the second row of this table. This refers to my second training example. With this notation, x2 is a 4-dimensional vector. In fact, more generally, this is an n-dimensional feature vector. With this notation, x2 is now a vector, and so I'm going to use also x
大家好，我是蔡志毅。那
j
2007
to
年的
denote
11
the
月，一个
value
在
of
意大
a
利
j
纽约的
of feature number j in the ith training example. So concretely, x2 subscript 3, let's say, would refer to feature number 3 in this vector, which is equal to 2. Right? And that was a 3 over there, just to fix my handwriting. So x2 subscript 3 is going to be equal to 2. Now that we have multiple features, let's talk about what the form of our hypothesis should be. Previously, this was the form of our hypothesis where x was our single feature. But now that we have multiple features, we aren't going to use this simple representation anymore. Instead, our form of the hypothesis in linear regression is going to be this. It's going to be theta 0 plus theta 1 x1 plus theta 2 x2 plus theta 3 x3 plus theta 4 x4. And if we have n features, then rather than summing up over our 4 features, we would have a sum over our n features. Concretely, for a particular setting of our parameters, we may have h of x equals at plus 0.1 x1 plus 0.01 x2 plus 3x3 minus 2 x4. This would be one example of a hypothesis. And you remember, a hypothesis is trying to predict the price of the house in thousands of dollars. This is saying that, you know, the base price of a house is maybe 80,000 plus another 0.1. So that's an extra, what, $100 per square feet. You know, plus the price goes up a little bit for each additional floor that the house has. So it's x2 was number of floors. And it goes out further for each additional bedroom the house has, because x3 was the number of bedrooms, and the price goes down a little bit with each additional age of the house, with each additional year of the age of the house. Here's the form of our hypothesis rewritten on the slide, and what I'm going to do is introduce a little bit of notation to simplify this equation. For convenience of notation, let me define x subscript 0 to be equal to 1. Concretely, this means that for every example I have a feature vector x superscript I, and x superscript I subscript 0 is going to be equal to 1. You can think of this as defining an additional 0 feature. So whereas previously I had n features, features x1, x2 through xn, I'm now defining an additional sort of 0 feature vector that always takes on the value of 1. So now my feature vector x becomes this n plus 1 dimensional vector that is 0 indexed. So this is now a n plus 1 dimensional feature vector, but I'm going to index it from 0. And I'm also going to think of my parameters as a vector. So my parameters here, right, that would be this theta 0, theta 1, theta 2, and so on up to theta n. I'm going to gather them up into a parameter vector written theta 0, theta 1, theta 2, and so on, down to theta n. This is another 0 index vector, so if index sign from 0, that is another n plus 1 dimensional vector. So my hypothesis can now be written theta 0 x0 plus theta 1 x1 plus dot 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 up to theta n xn. And this equation is the same as this one on top, because, you know, x0 is equal to 1. And the neat thing is I can now take this form of the hypothesis and write this as theta transpose x. Depending on how familiar you are with inner products of vectors, if you write out what theta transpose x is, what theta transpose x is there's theta 0, theta 1 up to theta n. So this thing here is theta transpose, and this is actually a n plus 1 by 1 matrix. It's also called a row vector. And we take that and multiply it with the vector x, which is x0, x1, and so on down to xn. And so the inner product, that is theta transpose x is just equal to this. This gives us a convenient way to write the form of the hypothesis as just the inner product between our parameter vector theta and our feature vector x, and it is this little bit of notation, this little extra bit of notational convention that let us write this in this compact form. So that's the form of our hypothesis when we have multiple features. And just to give this another name, this is also called multivariate linear regression. And the term multivariate is just maybe a fancy term for saying that we have multiple features or multiple variables with which to try to predict the value y. In the previous video, we talked about the form of the hypothesis for linear regression with multiple features, with multiple variables. In this video, let's talk about how to fit the parameters of that hypothesis. In particular, let's talk about how to use gradient descent for linear regression with multiple features. To quickly summarize our notation, this is our form of hypothesis in multivariate linear regression, where we'd adopted the convention that x0 equals 1. The parameters of this model are theta 0 through theta n, but instead of thinking of this as n separate parameters, which is valid, I'm instead going to think of the parameters as theta, where theta here is a n+1 dimensional vector. So I'm just going to think of the parameters of this model as itself being a vector. Our cost function is j of theta 0 through theta n, which is given by this usual sum squared error term. But again, instead of thinking of j as a function of these n+1 numbers, I'm going to more commonly write j as just a function of the parameter vector theta, so that theta here is a vector. Here's what gradient descent looks like. We're going to repeatedly update each parameter theta j according to theta j minus alpha times this derivative term. And once again, let me just write this as j of theta. So theta j is updated as theta j minus the learning rate alpha times the derivative or partial derivative of the cost function with respect to the parameter theta j. Let's see what this looks like when we implement gradient descent, and in particular, let's go see what that partial derivative term looks like. Here's what we have for gradient descent for the case of when we had n equals 1 feature. We had two separate update rules for the parameters theta 0 and theta 1, and hopefully these look familiar to you. And this term here was, of course, the partial derivative of the cost function with respect to the parameter theta 0. And similarly, we had a different update rule for the parameter theta 1. There was one little difference, which was that when we previously had only one feature, we would call that feature xi, but now in our new notation, we would of course call this x superscript I subscript 1 to denote our one feature. So that was for when we had only one feature. Let's look at the new algorithm for we have more than one feature, when the number of features n may be much larger than 1. We get this update rule for gradient descent. And maybe for those of you that know calculus, if you take the definition of the cost function and take the partial derivative of the cost function j with respect to the parameter theta j, you find that that partial derivative is exactly that term that I've just drawn the blue box around. And if you implement this, you will get a working implementation of gradient descent for multivariate linear regression. The last thing I want to do on this slide is give you a sense of why these new and old algorithms are, sort of the same thing, or why they're both similar algorithms, or why they're both gradient descent algorithms. Let's consider a case where we have two features, or maybe more than two features. So we have three update rules for the parameters theta 0, theta 1, theta 2, and maybe other values of theta as well. If you look at the update rule for theta 0, what you find is that this update rule here is the same as the update rule that we had previously for the case of n equals 1. And the reason that they're equivalent is, of course, because in our notational convention, we had this x0 equals 1 convention, which is why these two terms that I've drawn the magenta boxes around are equivalent. Similarly, if you look at the update rule for theta 1, you find that this term here is equivalent to the term we previously had the equation, the update rule we previously had for theta 1, where of course we're just using this new notation x subscript 1 to denote our new notation for denoting the first feature. And now that we have more than one feature, we can have similar update rules for the other parameters like theta 2 and so on. There's a lot going on the slides, so I definitely encourage you, if you need to pause the video and look at all the math on the slide slowly to make sure you understand everything that's going on here. But if you implement the algorithm written up here, then you will have a working implementation of linear regression with multiple features. In this video and in the video after this one, I want to tell you about some of the practical tricks for making gradient descent work well. In this video, I want to tell you about an idea called feature scaling. Here's the idea. If you have a problem where you have multiple features, if you make sure that the features are on a similar scale, by which I mean make sure that the different features take on similar ranges of values, then gradient descent can converge more quickly. Concretely, let's say you have a problem with two features where x1 is the size of a house and takes on values between, say, 0 to 2000, and x2 is the number of bedrooms, and maybe that takes on values between 1 and 5. If you plot the contours of the cost function j of theta, then the contours may look like this, where, let's see, j of theta is a function of parameters theta 0, theta 1, and theta 2. I'm going to ignore theta 0, so let's forget about theta 0 and pretend it's a function of only theta 1 and theta 2. But if x1 can take on a much larger range of values than x2, it turns out that the contours of the cost function j of theta can take on this sort of a very, very skewed elliptical shape. Except that with a sort of 2000 to 5 ratio, it can be even more skewed. So this very, very tall and skinny ellipses, or these very tall, skinny ovals can form the contours of the cost function j of theta. And if you run gradient descent on this sort of cost function, your gradients may end up taking a long time and can sort of oscillate back and forth, and it can take a long time before it can finally find its way to the global minimum. In fact, you can imagine if these contours were exaggerated even more, if we were to draw incredibly skinny, tall, skinny contours, and it can be even more extreme than that, then gradient descent can just, well, it turns out gradient descent will just have a much harder time taking its way, meandering around. It can take a long time to find its way to the global minimum. In these settings, a useful thing to do is to scale the features. Concretely, if you instead define the feature x1 to be the size of the house divided by 2000 and define x2 to be maybe the number of bedrooms divided by 5, then the contours of the cost function j can become much less skewed, so that the contours may look more like circles. And if you run gradient descent on a cost function like this, then gradient descent, you can show mathematically, can find a much more direct path to the global minimum rather than taking a much more convoluted path where it's sort of trying to follow a much more complicated trajectory to get to the global minimum. So by scaling the features so that they take on similar ranges of values, in this example we end up with both features x1 and x2 between 0 and 1. You can wind up with an implementation of gradient descent that can converge much faster. More generally, when we're performing feature scaling, what we often want to do is get every feature into approximately a -1 to +1 range. And concretely, your feature x0, that's always equal to 1, so that's already in that range. But you may end up dividing other features by different numbers to get them into this range. And the numbers -1 and +1 aren't too important. So if you have a feature, x1, that winds up being between 0 and 3, say, that's not a problem. Or if you end up having a different feature that winds up being between, -2 and positive 0.5, again, this is close enough to -1 and +1 that, that's fine. I think that's fine. It's only if you have a different feature, say x3, that is between, say, that ranges from minus 100 to plus 100, then this is a very different range of values than minus 1 and plus 1. So this might be a less well-scaled feature. And similarly, if your features take on a very, very small range of values, so if x4 takes on values between minus 0.0001 and positive 0.0001, then again, this takes on a much smaller range of values than the minus 1 to plus 1 range. And again, I would consider this feature poorly scaled. So you want the range of values, it can be a bit bigger than plus 1, a bit smaller than plus 1, but just not much bigger like plus 100 here, and not too much smaller like 0.001 over there. Different people have different rules of thumb, but the one that I use is that if a feature takes on a range of values from, say, minus 3 to plus 3, I usually think that should be just fine. But maybe if it takes on much larger values than plus 3 or minus 3, I might start to worry. And if it takes on values from, say, minus 1/3 to 1/3, I think that's fine too, or 0 to 1/3, or minus 1/3 to 0. That's typical range of values I consider okay. But if it takes on a much tinier range of values like x4 here, then again I might start to worry. So the take-home message is don't worry if your features are not exactly on the same scale or exactly in the same range of values, but so long as they're all close enough to this, gradient descent should work okay. In addition to dividing by sort of the maximum value, when performing feature scaling, sometimes people will also do what's called mean normalization. And what I mean by that is that you might take a feature xi and replace it with xi minus mu I to make your features have approximately 0 mean. And obviously we won't apply this to the feature x0 because the feature x0 is always equal to 1, so it cannot have an average of value of 0. But concretely, for other features, if the range of sizes of a house takes on values between 0 to 2000, and if the average size of a house is equal to 1000, then you might use this formula, set the feature x1 to be the size minus the average value divided by 2000. And similarly, if on average, if your houses have 1 to 5 bedrooms, and if on average a house has, say, 2 bedrooms, then you might use this formula to mean normalize your second feature x2. In both of these cases, you therefore wind up with features x1 and x2 that can take on values roughly between minus 0.5 and positive 0.5. It's actually not true. x2 can actually be slightly larger than 0.5, but close enough. And the more general rule is that you might take a feature x1 and replace it with x1 minus mu1 over s1, where to define these terms, mu1 is the average value of x1 in the training set, and s1 is the range of values of that feature. And by range, I mean, let's say, the maximum value minus the minimum value. Or for those of you that know what the standard deviation of a variable is, setting s1 to be the standard deviation of the variable would be fine too. But taking this max minus min would be fine. And similarly, for the second feature, x2, you replace x2 with this sort of subtract the mean of the feature and divide it by the range of values, meaning the max minus min. And this sort of formula will get your features, maybe not exactly, but maybe roughly into these sorts of ranges. And by the way, for those of you that are being super careful, technically, if we're taking the range as max minus min, this 5 here would actually become a 4. So if max is 5, min is 1, then the range of bedroom values is actually equal to 4. But all of these are approximate, and any value that gets the features into anything close to these sorts of ranges will do fine. And the feature scaling doesn't have to be too exact in order to get gradient descent to run quite a lot faster. So now you know about feature scaling, and if you apply this simple trick, it can make gradient descent run much faster and converge in a lot fewer iterations. That was feature scaling. In the next video, I'll tell you. In this video, I want to give you more practical tips for getting gradient descent to work. The ideas in this video will center around the learning rate alpha. Concretely, here's the gradient descent update rule, and what I want to do in this video is tell you about what I think of as debugging and some tips for making sure that gradient descent is working correctly. And second, I want to tell you how to choose the learning rate alpha, or at least how I go about choosing it. Here's something that I often do to make sure that gradient descent is working correctly. The job of gradient descent is to find a value of theta for you that hopefully minimizes the cost function j of theta. What I often do is therefore plot the cost function j of theta as gradient descent runs. So the x-axis here is the number of iterations of gradient descent, and as gradient descent runs, you hopefully get a plot that maybe looks like this. Notice that the x-axis is number of iterations. Previously, we were looking at plots of j of theta where the x-axis, where the horizontal axis, was the parameter vector theta. But this is not what this is. Concretely, what this point is I'm going to run gradient descent for 100 iterations, and whatever value I get for theta after 100 iterations, I'm going to get some value theta after 100 iterations, and I'm going to evaluate the cost function j of theta for the value of theta I get after 100 iterations, and this vertical height is the value of j of theta for the value of theta I got after 100 iterations of gradient descent. And this point here, that corresponds to the value of j of theta for the theta that I get after I've run gradient descent for 200 iterations. So what this plot is showing is it's showing the value of your cost function after each iteration of gradient descent, and if gradient descent is working properly, then j of theta should decrease after every iteration. And one useful thing that this sort of plot can tell you also is that if you look at the specific figure that I've drawn, it looks like by the time you've gotten out to maybe 300 iterations, between 300 and 400 iterations in this segment, it looks like j of theta hasn't gone down much more. So by the time you get to 400 iterations, it looks like this curve has flattened out here. And so way out here at 400 iterations, it looks like gradient descent has more or less converged because your cost function isn't going down much more. So looking at this figure can also help you judge whether or not gradient descent has converged. By the way, the number of iterations that gradient descent takes to converge for a particular application can vary a lot. So maybe for one application, gradient descent may converge after just 30 iterations. For a different application, gradient descent may take 3,000 iterations. For another algorithm, for another learning algorithm, it may take 3 million iterations. It turns out to be very difficult to tell in advance how many iterations gradient descent needs to converge, and is usually by plotting this sort of plot. Plotting the cost function as we increase the number of iterations is usually by looking at these plots that I try to tell if gradient descent has converged. It's also possible to come up with automatic convergence tests, namely to have an algorithm try to tell you if gradient descent has converged. And here's maybe a pretty typical example of an automatic convergence test. And such a test may declare convergence if your cost function j of theta decreases by less than some small value epsilon, some small value 10 to the minus 3 in one iteration. But I find that usually choosing what this threshold is pretty difficult, and so in order to check your gradient descent is converged, I actually tend to look at plots like these, like this figure on the left, rather than rely on an automatic convergence test. Looking at this sort of figure can also tell you or give you an advance warning if maybe gradient descent is not working correctly. Concretely, if you plot j of theta as a function of the number of iterations, then, if you see a figure like this where j of theta is actually increasing, then that gives you a clear sign that gradient descent is not working. And a figure like this usually means that you should be using a learning rate alpha. If j of theta is actually increasing, the most common cause for that is if you're maybe trying to minimize a function that maybe looks like this. But if your learning rate is too big, then if you start off there, gradient descent may overshoot the minimum and send you there. And if the learning rate is too big, you may overshoot again and then send you there, and so on. So that, what you really wanted was for it to start here and for it to slowly go downhill, right? But if the learning rate is too big, then gradient descent can instead, keep on overshooting the minimum so that you actually end up getting worse and worse, so sort of getting to higher values of the cost function j of theta, so that you end up with a plot like this. And if you see a plot like this, the fix usually is to just use a smaller value of alpha. Oh, and also, of course, make sure that your code does not have a bug in it. But usually, too large a value of alpha is the most common. Could be a common problem. Similarly, sometimes you may also see j of theta do something like this. And we go down for a while, then go up, then go down for a while, then go up, go down for a while, go up, and so on. And the fix for something like this is also to use a smaller value of alpha. I'm not going to prove it here, but under mild assumptions about the cost function j, which does hold true for linear regression, you can show, or mathematicians have shown, that if your learning rate alpha is small enough, then j of theta should decrease on every single iteration. So if this doesn't happen, it probably means alpha is too big and you should set it smaller. But of course, you also don't want your learning rate to be too small, because if you were to do that, then gradient descent can be slow to converge. And if alpha were too small, you might end up starting out here, say, and end up taking just minuscule baby steps, right? And just taking a lot of iterations before you finally get to the minimum. And so if alpha is too small, gradient descent can make very slow progress and be slow to converge. To summarize, if the learning rate is too small, you can have a slow convergence problem. And if the learning rate is too large, j of theta may not decrease on every iteration, and it may not even converge. In some cases, if the learning rate is too large, slow convergence is also possible. But the more common problem you see is that j of theta may not decrease on every iteration. And in order to debug all of these things, often plotting that j of theta as a function of the number of iterations can help you figure out what's going on. Concretely, what I actually do when I run gradient descent is I would try a range of values. So just try running gradient descent with a range of values for alpha, like 0.001, 0.01. So these are a factor of 10 differences. And for these different values of alpha, just plot j of theta as a function of number of iterations. And then pick the value of alpha that seems to be causing j of theta to decrease rapidly. In fact, what I do actually isn't these steps of 10. So this is a scale factor of 10 if each step up. What I actually do is try this range of values, and so on, where this is 0.001. I'll then increase the learning rate threefold to get 0.03, and then this step up, this is another roughly threefold increase from 0.03 to 0.01, and so these are roughly trying out gradient descent with each value I try being about 3x bigger than the previous value. So what I'll do is try a range of values until I've made sure that I found one value that's too small and make sure I found one value that's too large, and then I sort of try to pick the largest possible value or just something slightly smaller than the largest reasonable value that I found. And when I do that, usually this gives me a good learning rate for my problem. And if you do this too, hopefully you'll be able to choose a good learning rate for your implementation of gradient descent. You now know about linear regression with multiple variables. In this video, I want to tell you a bit about the choice of features that you have and how you can get different learning algorithms, sometimes very powerful ones, by choosing appropriate features. And in particular, I also want to tell you about polynomial regression, which allows you to use the machinery of linear regression to fit very complicated, even very nonlinear functions. Let's take the example of predicting the price of a house. Suppose you have two features, the frontage of the house and the depth of the house. So here's a picture of the house we're trying to sell. The frontage is defined as this distance. It's basically the width or the length of how wide your lot is, of this plot of land that you own. And the depth of the house is how deep your property is. So there's the frontage, that's the depth. So you have two features called frontage and depth. You might build a linear regression model like this, where frontage is your first feature x1 and depth is your second feature x2. But when you're applying linear regression, you don't necessarily have to use just the features x1 and x2 that you're given. What you can do is actually create new features by yourself. So if I want to predict the price of a house, what I might do instead is decide that what really determines the size of a house is the area, really the land area that I own. So I might create a new feature. I'm just call this feature x, which is frontage times depth. This is a multiplication symbol, right? So frontage times depth, because this is the land area that I own, and I might then select my hypothesis as that, using just one feature, which is my land area, right? Because the area of a rectangle is, the product of the length of a size. So depending on what insight you might have into a particular problem, rather than just taking the features, frontage, and depth that we happen to have started off with, sometimes by defining new features, you might actually get a better model. Closely related to the idea of choosing your features is this idea called polynomial regression. Let's say you have a housing price data set that looks like this. Then there are a few different models you might fit to this. One thing you could do is fit a quadratic model like this. It doesn't look like a straight line fits this data very well. So maybe you want to fit a quadratic model like this, where you think the price is a quadratic function, and maybe that will give you, a fit to the data that looks like that. But then you might decide that quadratic model doesn't make sense, because with a quadratic function, eventually this function comes back down, and well, we don't think housing prices should go down when the size goes up too high. So then maybe we might choose a different polynomial model and choose to use instead a cubic function, and where we have now a third order term, and we fit that, maybe we would get this sort of model. And maybe the green line is a somewhat better fit to the data because it doesn't eventually come back down. So how do we actually fit a model like this to our data? Using the machinery of multivariate linear regression, we can do this with a pretty simple modification to our algorithm. The form of the hypothesis we know how to fit looks like this, where we say that h of x is theta 0 plus theta 1 x1 plus theta 2 x2 plus theta 3 x3. And if we want to fit this cubic model that I have boxed in green, what we're saying is that the predicted price of a house is theta 0 plus theta 1 times the size of the house, plus theta 2 times the square size of the house, so this term is equal to that term, and then plus theta 3 times the cube of the size of the house, right? So it's that third term. In order to map these two definitions to each other, well, the natural way to do that is to set the first feature x1 to be the size of the house, and set the second feature x2 to be the square of the size of the house, and set the third feature x3 to be the cube of the size of the house. And just by choosing my three features this way and applying the machinery of linear regression, I can fit this model and end up with a cubic fit to my data. I just want to point out one more thing, which is that if you choose your features like this, then feature scaling becomes increasingly important. So if the size of a house ranges from 1 to 1,000, so from 1 to 1,000 square feet, say, then the size squared of the house will range from 1 to 1 million. That's the square of 1,000, and your third feature x cubed, your third feature x3, which is the size cubed of the house, will range from 1 to 10 to the 9. And so these three features take on very different ranges of values, and it's important to apply feature scaling if you're using gradient descent to get them into comparable ranges of values. Finally, here's one last example of how you really have broad choices in the features you use. Earlier, we talked about how a quadratic model like this might not be ideal because, maybe a quadratic model fits the data okay, but the quadratic function goes back down, and we really don't want, housing prices that go down to predict that as the size of the house increases. But rather than going to a cubic model, you have maybe other choices of features, and there are many possible choices. But just to give you another example of a reasonable choice, another reasonable choice might be to say that the price of a house is theta 0 plus theta 1 times the size, and then plus theta 2 times the square root of the size, right? So the square root function is this sort of function, and maybe there will be some value of theta 1, theta 2, theta 3 that will let you take this model and fit a curve that looks like that, and goes up but doesn't, but sort of flattens out a bit and doesn't ever come back down. And so by having insight into, in this case, the shape of the square root function, and into the shape of the data by choosing different features, you can sometimes get better models. In this video, we talked about polynomial regression, that is, how to fit a polynomial like a quadratic function or a cubic function to your data. And we talked about this idea that you have a choice in what features to use, such as that instead of using the frontage and the depth of a house, maybe you can multiply them together to get a feature that captures the land area of a house. In case this seems a little bit bewildering, that, wow, we have all these different feature choices, so how do I decide what features to use? Later in this class, we'll talk about some algorithms for automatically choosing what features to use, so that you can have an algorithm look at the data and automatically choose for you whether you want to fit a quadratic function or a cubic function or something else. But until we get to those algorithms, for now, I just want you to be aware that you have a choice in what features to use. And by designing different features, you can fit more complex functions to your data than just fitting a straight line to the data. And in particular, you can fit polynomial functions as well. And sometimes by appropriate insights into the features, you can get a much better model for your data. In this video, we'll talk about the normal equation, which for some linear regression problems will give us a much better way to solve for the optimal value of the parameters theta. Concretely, so far, the algorithm that we've been using for linear regression is gradient descent, where in order to minimize the cost function j of theta, we would take this iterative algorithm that takes many steps, so multiple iterations of gradient descent, to converge to the global minimum. In contrast, the normal equation will give us a method to solve for theta analytically, so that rather than needing to run this iterative algorithm, we can instead just solve for the optimal value for theta all in one go, so that in basically one step, you get to the optimal value right there. It turns out the normal equation method has some advantages and some disadvantages, but before we get to that and talk about when you should use it, let's get some intuition about what this method does. For this explanatory example, let's take a very simplified cost function j of theta that's just a function of a row number theta. So for now, imagine that theta is just a scalar value, or that theta is just a row value. It's just a number rather than a vector. Imagine that we have a cost function j that's a quadratic function of this row-valued parameter theta. So j of theta looks like that. Well, how do you minimize a quadratic function? For those of you that know a little bit of calculus, you may know that the way to minimize a function is to take derivatives and to set derivatives equal to 0. So if you take the derivative of j with respect to the parameter theta, you get some formula, which I'm not going to derive, and then you set that derivative equal to 0, and this allows you to solve for the value of theta that minimizes j of theta. That was the simpler case of when theta is just a row number. In the problem that we're interested in, theta is no longer just a row number, but instead is this n+1 dimensional parameter vector. And our cost function j is a function of this vector value, or theta 0 through theta m, and the cost function looks like this sum squared cost function on the right. How do we minimize this cost function j? Calculus actually tells us that one way to do so is to take the partial derivative of j with respect to every parameter theta j in turn, and then to set all of these to 0. If you do that and you solve for the values of theta 0, theta 1 up to theta n, then this will give you the values of theta that minimize the cost function j. But if you actually work through the calculus and work through the solution to the parameters theta 0 through theta n, the derivation ends up being somewhat involved. And what I'm going to do in this video is actually to not go through the derivation, which is kind of long and kind of involved. But what I want to do is just tell you what you need to know in order to implement this process so that you can solve for the values of the thetas that corresponds to where the partial derivative is equal to 0, or alternatively, or equivalently, the values of thetas that minimize the cost function j of theta. And I realize some of the comments I may have made more sense only to those of you that are a little more familiar with calculus. So, but if you don't know, if you're less familiar with calculus, don't worry about it. I'm just going to tell you what you need to know in order to implement this algorithm and get it to work. For the example that I want to use as a running example, let's say that I have m equals 4 training examples. In order to implement this normal equation method, what I'm going to do is the following. I'm going to take my data set. So here are my 4 training examples. In this case, let's assume that these 4 examples is all the data I have. Okay. What I'm going to do is take my data set and add an extra column that corresponds to my extra feature x0 that's always takes on this value of 1. What I'm going to do is I'm then going to construct a matrix called capital X. That's a matrix that basically contains all of the features for my training data. So concretely, here are all my features. I'm going to take all those numbers and put them into this matrix X. Okay, so just copy the data over one column at a time. And then I'm going to do something similar for y. So I'm going to take the values I'm trying to predict and construct now a vector, like so, and call that a vector y. So x is going to be a m by n plus 1 dimensional matrix, and y is going to be a m dimensional vector, where m is the number of training examples and n is the number of features. And I have n plus 1 because of this extra feature x0 that I added. Finally, if you take your matrix X and you take your vector Y, and if you just compute this and set theta to be equal to x transpose x inverse times x transpose y, this will give you the value of theta that minimizes your cost function. There was a lot that happened on this slide, and I worked through it using one specific example of one data set. Let me just write this out in a slightly more general form, and then later on in this video, let me explain this equation a little bit more in case it's not yet entirely clear how to do this. In the general case, let's say we have m training examples, so x1, y1 up to xm, ym, and n features. So each of our training examples, xi, may look like a vector like this. There's an n plus 1 dimensional feature vector. The way I'm going to construct the matrix X, this is also called the design matrix, is as follows. Each training example gives me a feature vector like this. That's this sort of n plus 1 dimensional vector. The way I'm going to construct my design matrix X is I'm going to construct a matrix like this. And what I'm going to do is take the first training example, so that's a vector, take its transpose, so it ends up being this long flat thing, and make x1 transpose the first row of my design matrix X. Then I'm going to take my second training example, x2, take the transpose of that, and put that as the second row of X, and so on, down until my last training example, take the transpose of that, and that's my last row of my matrix X. And so this makes my matrix X an m by n plus 1 dimensional matrix. As a concrete example, let's say I have only one feature, only one feature other than x0, which is always equal to 1. So if my feature vectors xi are equal to this 1, which is x0, and then some row feature like maybe the size of the house, then my design matrix X would be equal to this. For the first row, I'm going to basically take this and take its transpose. So I'm going to end up with 1, and then x1, 1. For the second row, I'm going to end up with 1, and then x1, 2, and so on down to 1, and then x1, m. and thus this will be a M by two-dimensional matrix. So that's how I construct the matrix X. And the vector Y, sometimes I might write an arrow on top to denote that it's a vector, but very often I'll just write this as Y either way. The vector Y is obtained by taking all the labels, all the correct prices of houses in my training set, and just stacking them up into an m-dimensional vector, and that's Y. Finally, having constructed the matrix X and the vector Y, we then just compute theta as X transpose X inverse times X transpose Y. I just want to make sure that this equation makes sense to you and that you know how to implement it. So, concretely, what is this X transpose X inverse? Well, X transpose X inverse is the inverse of the matrix X transpose X. Concretely, if you were to say set A to be equal to X transpose times X, so X transpose is a matrix, X transpose times X gives you another matrix, and we'll call that matrix A, then, X transpose X inverse is just, you take this matrix A and you invert it, right? Let's equal to, let's say, A inverse, and so that's how you compute this thing. You compute X transpose X, and then you compute this inverse. We haven't yet talked about octave. We'll do so in a later set of videos, but in the octave programming language, or similarly in also the MATLAB programming language is very similar. The command to compute this quantity, I guess really this quantity, X transpose X inverse times X transpose Y, is as follows. In octave, X prime is the notation that you use to denote X transpose, and so this expression that's boxing in red, that's computing X transpose times X. P_inv is a function for computing the inverse of a matrix, so this computes X transpose X inverse, and then you multiply that by X transpose, and you multiply that by Y, so you end up computing that formula, which I didn't prove, but it is possible to show mathematically, even though I'm not going to do so here. That this formula gives you the optimal value of theta, in the sense that this, if you set theta equal to this, that's the value of theta that minimizes the cost function j of theta for linear regression. One last detail. In an earlier video, I talked about feature scaling and the idea of getting features to be on similar ranges of scales, or similar ranges of values of each other. If you're using this normal equation method, then feature scaling isn't actually necessary, and is actually okay if, say, some feature x1 is between 0 and 1, and some feature x2 is between, ranges from 0 to 1000, and some feature x3 ranges from 0 to 10 to the minus 5. And if you're using the normal equation method, this is okay, and there's no need to do feature scaling. Although, of course, if you were using gradient descent, then feature scaling is still important. Finally, when should you use gradient descent, and when should you use the normal equation method? Here are some of their advantages and disadvantages. Let's say you have m training examples and n features. One disadvantage of gradient descent is that you need to choose the learning rate alpha, and often this means running it a few times with different learning rate alphas and then seeing what works best. And so that's a lot of extra work and extra hassle. Another disadvantage of gradient descent is that it needs many iterations, and so depending on the details, that could make it slower, although there's more to the story, as we'll see in a second. As for the normal equation, you don't need to choose any learning rate alpha, so that makes it really convenient, makes it simpler to implement, and you just run it, and it just usually just works. And you don't need to iterate, so you don't need to plot j of theta, check for convergence, and take all those extra steps. So far, the balance seems to favor the normal equation. Here are some disadvantages of the normal equation and some advantages of gradient descent. Gradient descent works pretty well even when you have a very large number of features. So even if you have millions of features, you can run gradient descent, and it'll be reasonably efficient, and it'll do something reasonable. In contrast, the normal equation, in order to solve for the parameters theta, we need to solve for this term. We need to compute this term X transpose X inverse. This matrix X transpose X, that's an n by n matrix if you have n features. because if you look at the dimensions of X transpose dimensions of X, you figure out what the dimension of the product is. The matrix X transpose X is an n by n matrix, where n is the number of features. And on most computer implementations, the cost of inverting a matrix grows roughly as the cube of the dimension of the matrix. So computing this inverse costs roughly order n cubed time. Sometimes it's slightly faster than n cubed, but it's close enough for our purposes. So if n is the number of features is very large, then computing this quantity can be slow, and the normal equation method can actually be much slower. So if n is large, then I might usually use gradient descent because we don't want to pay this order n cubed time. But as n is relatively small, then the normal equation might give you a better way to solve the parameters. What does small and large mean? Well, if n is on the order of 100, then inverting a 100 by 100 matrix is no problem by modern computing standards. If n is 1,000, I would still use the normal equation method. Inverting a 1,000 by 1,000 matrix is actually really fast in a modern computer. If n is 10,000, then I might start to wonder. Inverting a 10,000 by 10,000 matrix starts to get kind of slow, and I might then start to maybe lean in the direction of gradient descent, but maybe not quite. N equals 10,000, you can sort of invert a 10,000 by 10,000 matrix. But if it gets much bigger than that, then I would probably use gradient descent. So if n equals 10 to the 6, if you have a million features, then inverting a million by million matrix, it's going to be very expensive, and I would definitely favor gradient descent if you have that many features. So exactly how large your set of features has to be before you convert to gradient descent, I don't know. It's hard to give a strict number, but for me, it's usually around 10,000. But I might start to consider switching over to gradient descent, or maybe to some other algorithms that we'll talk about later in this class. To summarize, so long as the number of features is not too large, the normal equation gives us a great alternative method to solve for the parameters data. Concretely, so long as the number of features is less than 1,000, I would usually just use the normal equation method rather than gradient descent. To preview some ideas that we'll talk about later in this course, as we get to the more complex learning algorithm, for example, when we talk about classification algorithms like a logistic regression algorithm, we'll see that those algorithms actually, the normal equation method actually do not work for those more sophisticated learning algorithms, and we will have to resort to gradient descent for those algorithms. So gradient descent is a very useful algorithm to know, both for linear regression when we have a large number of features, and for some of the other algorithms that we'll see in this course, because for them the normal equation method just doesn't apply, it doesn't work. But for the specific model of linear regression, the normal equation can give you a alternative that can be much faster than gradient descent. And so depending on the details of your algorithm, depending on the details of your problem and how many features you have, both of these algorithms are well worth knowing about. You now know. In this video, I want to talk about the normal equation and non-invertibility. This is a somewhat more advanced concept, but it's something that I've often been asked about, and so I want to talk about here and address it here. But this is a somewhat more advanced concept, so feel free to consider this optional material. And it's a phenomenon that you may run into that's maybe somewhat useful to understand, but even if you don't understand the normal equation and linear regression, you should really get that to work okay. Here's the issue. For those of you that are maybe somewhat more familiar with linear algebra, what some students have asked me is, when computing this theta equals x transpose x inverse x transpose y, what if the matrix x transpose x is non-invertible? So for those of you that know a bit more linear algebra, you may know that only some matrices are invertible and some matrices do not have an inverse. We call those non-invertible matrices singular or degenerate matrices. The issue or the problem of x transpose x being non-invertible should happen pretty rarely. And in Octave, if you implement this to compute theta, it turns out that this will actually do the right thing. I'm getting a little technical now, and I don't want to go into the details, but Octave has two functions for inverting matrices. One is called pinf, and the other is called inv. And the differences between these two are somewhat technical. One's called the pseudo-inverse, one's called the inverse. But you can show mathematically that so long as you use the p-in function, then this will actually compute the value of theta that you want, even if x transpose x is non-invertible. The specific details between what is the difference between p-inv and what is inv, that's somewhat advanced numerical computing concepts that I don't really want to get into. But I thought in this optional video, I'll try to give you a little bit of intuition about what it means for x transpose x to be non-invertible, for those of you that know a bit more linear algebra and might be interested. I'm not going to prove this mathematically, but if x transpose x is non-invertible, there are usually two most common causes for this. The first cause is if somehow in your learning problem you have redundant features. Concretely, if you're trying to predict housing prices, and if x1 is the size of the house in feet, in square feet, and x2 is the size of the house in square meters, then 1 meter is equal to 3.28 feet. Rounded to 2 decimals, and so your two features will always satisfy the constraint that x1 equals 3.28 squared times x2. And you can show, for those of you that are this is somewhat advanced linear algebra now, but if you're an expert in linear algebra, you can actually show that if your two features are related via a linear equation like this, then the matrix x transpose x will be non-invertible. The second thing that can cause x transpose x to be non-invertible is if you're trying to run a learning algorithm with a lot of features. Concretely, if m is less than or equal to n. For example, if you imagine that you have m equals 10 training examples, but you have n equals 100 features, then you're trying to fit a parameter vector theta, which is n plus 1 dimensional, so it's 101 dimensional. You're trying to fit 101 parameters from just 10 training examples. And this turns out to sometimes work, but to not always be a good idea, because as we'll see later, you might not have enough data if you have only 10 examples to fit 100 or 101 parameters. We'll see later in this course why this might be too little data to fit this many parameters. But commonly what we do then, if m is less than n, is to see if we can either delete some features or to use a technique called regularization, which is something that we'll talk about later in this course as well, that will kind of let you fit a lot of parameters, use a lot of features, even if you have a relatively small training set. But this regularization will be a later topic in this course. But to summarize, if ever you find that x transpose x is singular, or alternatively you find it is non-invertible, what I would recommend you do is first look at your features and see if you have redundant features like this x1, x2, being linearly dependent or being a linear function of each other like so. And if you do have redundant features, and if you just delete one of these features, you really don't need both of these features. If you just delete one of these features, that would solve your non-invertibility problem. And so I would first think through my features and check if any are redundant, and if so, then keep deleting redundant features until they're no longer redundant. And if your features are not redundant, I would check if I might have too many features, and if that's the case, I would either delete some features if I can bear to use fewer features, or else I would consider using regularization, which is this topic that we'll talk about later. So that's it for the normal equation and what it means for if the matrix x transpose x is non-invertible. But this is a problem that you should run, that hopefully you run into pretty rarely. And if you just implement it in Octave using the p-in function, which is called the pseudo-inverse function. So if you use a different linear algebra library, it's called a pseudo-inverse. But that implementation should just do the right thing, even if x transpose x is non-invertible, which should happen pretty rarely anyway, so this should not be a problem for most implementations of linear regression. In this video, we'll talk.
Okay, guys, so we do exhaustive linear regression with single variable, with multiple variables. And now we'll move to one of this is for estimation and the prediction. This is for prediction as a supervised machine learning technique, because we said we have both, either prediction for values, or classes. If we wanted to predict the classes, we call it a classification problem. And this we will start with a technique also connected to regression, but called logistic regression. And this algorithm is used for classification as a supervised machine learning classification algorithm. So we will start with it. By the way, all the handout and the link for this video series is available in our. So we will start with logistic regression now.
In this and the next
as one of the first classification algorithm for classification for supervised machine learning techniques.
Few videos, I want to start to talk about classification problems where the variable y that you want to predict is discrete valued. We'll develop an algorithm called logistic regression, which is one of the most popular and most widely used learning algorithms today. Here are some examples of classification problems. Earlier we talked about email spam classification as an example of a classification problem. Another example would be classifying online transactions. So if you have a website that sells stuff and if you want to know if a particular transaction is fraudulent or not, whether someone has, is using a stolen credit card or has stolen the user's password, that's another classification problem. And earlier we also talked about the example of classifying tumors as cancerous, malignant, or as benign tumors. In all of these problems, the variable that we're trying to predict is a variable y that we can think of as taking on two values, either 0 or 1, either spam or not spam, fraudulent or not fraudulent, malignant or benign. Another name for the class that we denote with 0 is the negative class, and another name for the class that we denote with 1 is the positive class. So 0 may denote the benign tumor, and 1 positive class may denote a malignant tumor. The assignment of the two classes, spam, not spam, and so on, the assignment of the two classes to positive and negative, to 0 and 1, is somewhat arbitrary, and it doesn't really matter. But often there is this intuition that the negative class is conveying the absence of something, like the absence of a malignant tumor, whereas 1, the positive class, is conveying the presence of something that we may be looking for. But the designation of which is negative and which is positive is somewhat arbitrary, and it doesn't matter that much. For now, we're going to start with classification problems with just two classes, 0 and 1. Later on, we'll talk about multi-class problems as well, where the variable y may take on, say, 4 values, 0, 1, 2, and 3. This is called a multi-class classification problem. But for the next few videos, let's start with the two-class or the binary classification problem, and we'll worry about the multi-class setting later. So how do we develop a classification algorithm? Here's an example of a training set for a classification task for classifying a tumor as malignant or benign. And notice that malignancy takes on only two values, 0 or no, 1 or yes. So one thing we could do, given this training set, is to apply the algorithm that we already know, linear regression, to this data set, and just try to fit a straight line to the data. So if you take this training set and fit a straight line to it, maybe you get a hypothesis that looks like that, right? So that's my hypothesis, h of x equals theta transpose x. If you want to make predictions, one thing you could try doing is then threshold the classifier output at 0.5, that is at the vertical axis value 0.5. And if the hypothesis outputs a value that's greater than or equal to 0.5, you predict y equals 1. If it's less than 0.5, you predict y equals 0. Let's see what happens if we do that. So let's take 0.5, and so, that's where the threshold is, and thus, using linear regression this way, everything to the right of this point, we would end up predicting as the positive class because the output values is greater than 0.5 on the vertical axis, and everything to the left of that point, we will end up predicting as a negative value. In this particular example, it looks like linear regression is actually doing something reasonable, even though this is a classification task we're interested in. But now let's try changing the problem a bit. Let me extend out the horizontal axis a little bit, and let's say we got one more training example way out there on the right. Notice that that additional training example, this one out here, it doesn't actually change anything, right? It's, looking at the training set, it's pretty clear what a good hypothesis is. It's that, well, everything to the right of somewhere around here, to the right of this, we should predict as positive, and everything to the left, we should probably predict as negative, because from this training set, it looks like all the tumors larger than, a certain value around here are malignant, and all the tumors smaller than that are not malignant, at least for this training set. But once we've added that extra example out here, if you now run linear regression, you will instead get a straight line fit to the data that might maybe look like this. And if you now threshold this hypothesis at 0.5, you end up with a threshold that's around here, so that everything to the right of this point you predict as positive, and everything to the left of that point you predict as negative. And this seems a pretty bad thing for linear regression to have done, right? Because, these are our positive examples, these are our negative examples. It's pretty clear we really should be separating the two clauses somewhere around there. But somehow, by adding one example way out here to the right, this example really isn't giving us any new information. I mean, it should be no surprise to the learning algorithm that the example way out here turns out to be malignant. But somehow adding that example out there caused linear regression to change its straight line fit to the data from this magenta line out here to this blue line over here, and caused it to give us a worse hypothesis. So applying linear regression to a classification problem usually isn't, or often isn't, a great idea. In the first instance, in the first example, before I added this extra training example, previously, linear regression was just getting lucky, and it got us a hypothesis that, worked well for that particular example. But usually applying linear regression to a data set, you might get lucky, but often it isn't a good idea. So I wouldn't use linear regression for classification problems. Here's one other funny thing about what would happen if we were to use linear regression for a classification problem. For classification, we know that y is either 0 or 1, but if you are using linear regression, well, the hypothesis can output values that are much larger than 1 or less than 0, even if all of your training examples have labels y equals 0 or 1. And it seems kind of strange that even though we know that the labels should be 0 or 1, it seems kind of strange if the algorithm can output values much larger than 1 or much smaller than 0. So what we'll do in the next few videos is develop an algorithm called logistic regression, which has the property that the output, the predictions of logistic regression, are always between 0 and 1 and doesn't become bigger than 1 or become less than 0. And by the way, logistic regression is, and we will use it as a classification algorithm, is maybe sometimes confusing that the term regression appears in its name, even though logistic regression is actually a classification algorithm, but that's just the name it was given for historical reasons. So don't be confused by that. Logistic regression is actually a classification algorithm that we apply to settings where the label y. Let's start talking about logistic regression. In this video, I'd like to show you the hypothesis representation. That is, what is the function we're going to use to represent our hypothesis when we have a classification problem. Earlier, we said that we would like our classifier to output values that are between 0 and 1. So we'd like to come up with a hypothesis that satisfies this property, that its predictions are maybe between 0 and 1. When we were using linear regression, this was the form of a hypothesis where h of x is theta transpose x. For logistic regression, I'm going to modify this a little bit and make the hypothesis g of theta transpose x, where I'm going to define the function g as follows. G of z, if z is a real number, is equal to 1 over 1 plus e to the negative z. This is called the sigmoid function, or the logistic function, and the term logistic function, that's what gives rise to the name logistic regression. And by the way, the terms sigmoid function and logistic function are basically synonyms and mean the same thing. So the two terms are basically interchangeable, and either term can be used to refer to this function g. And if we take these two equations and put them together, then here's just an alternative way of writing out the form of my hypothesis. I'm saying that h of x is 1 over 1 plus e to the negative theta transpose x. And all I've done is I've taken this variable z here is a real number, and plugged in theta transpose x. So I end up with, theta transpose x in place of z there. Lastly, let me show you what the sigmoid function looks like. I'm going to plot it on this figure here. The sigmoid function, g of z, also called the logistic function, it looks like this. It starts off near 0, and then it rises until it crosses 0.5 at the origin, and then it flattens out again like so. So that's what the sigmoid function looks like. And you notice that the sigmoid function, well, it asymptotes at 1, and it asymptotes at 0 as z, I guess the horizontal axis is z. As z goes to minus infinity, g of z approaches 0. And as g of z approaches infinity, g of z approaches 1. And so because g of z outputs values that are between 0 and 1, we also have that h of x must be between 0 and 1. Finally, given this hypothesis representation, what we need to do, as before, is fit the parameters theta to our data. So given a training set, we need to pick a value for the parameters theta, and this hypothesis will then let us make predictions. We'll talk about a learning algorithm later for fitting the parameters theta. But first, let's talk a bit about the interpretation of this model. Here's how I'm going to interpret the output of my hypothesis h of x. When my hypothesis outputs some number, I am going to treat that number as the estimated probability that y is equal to 1 on a new input, example x. Here's what I mean. Here's an example. Let's say we're using the tumor classification example. So we may have a feature vector x, which is this x0 equals 1 as always, and then our one feature is the size of the tumor. Suppose I have a patient come in and they have some tumor size, and I feed their feature vector x into my hypothesis, and suppose my hypothesis outputs the number 0.7. I'm going to interpret my hypothesis as follows. I'm going to say that this hypothesis is telling me that for a patient with features x, the probability that y equals 1 is 0.7. In other words, I'm going to tell my patient that their tumor, sadly, has a 70% chance or a 0.7 chance of being malignant. To write this out slightly more formally, or to write this out in math, I'm going to interpret my hypothesis output as p of y equals 1 given x parameterized by theta. So for those of you that are familiar with probability, this equation may make sense. If you're a little less familiar with probability, here's how I read this expression. This is the probability that y is equal to 1 given x, so given that my patient has features x, or given my patient has a particular tumor size represented by my features x, and this probability is parameterized by theta. So I'm basically going to count on my hypothesis to give me estimates of the probability that y is equal to 1. Now, since this is a classification task, we know that y must be either 0 or 1, right? Those are the only two values that y could possibly take on, either in the training set or for new patients that may walk into my office or into the doctor's office in the future. So given h of x, we can therefore compute the probability that y is equal to 0 as well. Concretely, because y must be either 0 or 1, we know that the probability of y equals 0 plus the probability of y equals 1 must add up to 1. This first equation looks a little bit more complicated, but it's basically saying that probability of y equals 0 for a particular patient with features x, and given our parameters theta, plus the probability of y equals 1 for that same patient with features x, and given our parameters theta, must add up to 1. if this equation looks a little bit complicated, feel free to mentally imagine it without that x and theta. And this is just saying that the probability of y equals 0 plus the probability of y equals 1 must be equal to 1. And we know this to be true because y has to be either 0 or 1. And so the chance of y being equal to 0 plus the chance that y is 1, those two must add up to 1. And so if you just take this term and move it to the right-hand side, then you end up with this equation. It says probability of y equals 0 is 1 minus probability of y equals 1. And thus, if our hypothesis, if h of x gives us that term, you can therefore quite simply compute the probability or compute the estimated probability that y is equal to 0 as well. So you now know what the hypothesis representation is for logistic regression. And we've seen what the mathematical formula is defining the hypothesis for logistic regression. In the next video, I'd like to try to give you better intuition about what the hypothesis function looks like. And I want to tell you about something called the decision boundary. And we'll look at some visualizations together to try to get a better sense of what this hypothesis function of logistic regression really looks like. In the last video, we talked about the hypothesis representation for logistic regression. What I'd like to do now is tell you about something called the decision boundary, and this will give us a better sense of what the logistic regression's hypothesis function is computing. To recap, this is what we wrote out last time, where we said that the hypothesis is represented as h of x equals g of theta transpose x, where g is this function called the sigmoid function, which looks like this. So it slowly increases from 0 to 1, asymptoting at 1. What I want to do now is try to understand better when this hypothesis will make predictions that y is equal to 1 versus when it might make predictions that y is equal to 0, and understand better what the hypothesis function looks like, particularly when we have more than one feature. Concretely, this hypothesis is outputting estimates of the probability that y is equal to 1, given x and parameterized by theta. So if we wanted to predict is y equal to 1 or is y equal to 0, here's something we might do. Whenever the hypothesis outputs that the probability of y being 1 is greater than or equal to 0.5, so this means that if it's more likely to be y equals 1 than y equals 0, then let's predict y equals 1. And otherwise, if the estimated probability of y being equal to 1 is less than 0.5, then let's predict y equals 0. And I chose a greater than or equal to here and a less than here. If h of x is equal to 0.5 exactly, then we could predict positive or negative, but I put a greater than or equal to 2 here, so we default maybe to predicting positive if h of x is 0.5, but that's a detail that really doesn't matter that much. What I want to do is understand better when is it exactly that h of x will be greater than or equal to 0.5, so that we'll end up predicting y is equal to 1. If we look at this plot of the sigmoid function, we'll notice that the sigmoid function, g of z, is greater than or equal to 0.5 whenever z is greater than or equal to 0. So it's in this half of the figure that g takes on values that are 0.5 and higher, right? Because this notch here, that's the 0.5. And so when z is positive, g of z, the sigmoid function, is greater than or equal to 0.5. Since the hypothesis for logistic regression is h of x equals g of theta transpose x, this is therefore going to be greater than or equal to 0.5 whenever theta transpose x is greater than or equal to 0. So what we've shown, right, because here theta transpose x takes the row of z. So what we've shown is that our hypothesis is going to predict y equals 1 whenever theta transpose x is greater than or equal to 0. Let's now consider the other case of when our hypothesis will predict y is equal to 0. Well, by a similar argument, h of x is going to be less than 0.5 whenever g of z is less than 0.5, because the range of values of z that cause g of z to take on values less than 0.5, well, that's when z is negative. So when g of z is less than 0.5, a hypothesis would predict that y is equal to 0. And by a similar argument to what we had earlier, h of x is equal to g of theta transpose x, and so we'll predict y equals 0 whenever this quantity theta transpose x is less than 0. To summarize what we just worked out, we saw that if we decide to predict whether y is equal to 1 or y is equal to 0, depending on whether the estimated probability is greater than or equal to 0.5 or whether it's less than 0.5, then that's the same as saying that we'll predict y equals 1 whenever theta transpose x is greater than or equal to 0, and we'll predict y is equal to 0 whenever theta transpose x is less than 0. Let's use this to better understand how the hypothesis of logistic regression makes its predictions. Now, let's suppose we have a training set like that shown on this slide. And suppose our hypothesis is h of x equals g of theta 0 plus theta 1 x1 plus theta 2 x2. We haven't talked yet about how to fit the parameters of this model. We'll talk about that in the next video. But suppose that via a procedure to be specified, we end up choosing the following values for the parameters. Let's say we choose theta 0 equals 3, theta 1 equals 1, theta 2 equals 1. So this means that my parameter vector is going to be theta equals minus 3, 1, 1.
So you're interested in machine learning, but you're not sure where to learn more about it. Check out TensorFlow, built by Google engineers and powering Google Tech. We've curated some of our favorite videos, courses, and books so you can get working with the very latest in machine learning. It's all on the Learn ML page at tensorflow.org.
So, given this choice of my hypothesis parameters, let's try to figure out where our hypothesis would end up predicting y equals 1 and where it would end up predicting y equals 0. Using the formulas that we worked out on the previous slide, we know that y equals 1 is more likely, that is, the probability that y equals 1 is greater than 0.5 or greater than or equal to 0.5 whenever theta transpose x is greater than 0. And this formula that I just underlined, minus 3 plus x1 plus x2, is, of course, theta transpose x when theta is equal to this value of the parameters that we just chose. So for any example with features x1 and x2 that satisfy this equation, that minus 3 plus x1 plus x2 is greater than or equal to 0, our hypothesis will think that y equals 1 is more likely, or will predict that y is equal to 1. We can also take minus 3 and bring this to the right and rewrite this as x1 plus x2 is greater than or equal to 3, and so equivalently we've found that this hypothesis will predict y equals 1 whenever x1 plus x2 is greater than or equal to 3. Let's see what that means on the figure. If I write down the equation x1 plus x2 equals 3, this defines the equation of a straight line. And if I draw what that straight line looks like, it gives me the following line, which passes through 3 and 3 on the x1 and the x2 axes. So the part of the input space, the part of the x1, x2 plane that corresponds to when x1 plus x2 is greater than or equal to 3, that's going to be this right half plane. That is everything to the up and everything to the upper right portion of this magenta line that I just drew. And so the region where our hypothesis will predict y equals 1 is this region, is really this huge region, this half space over to the upper right. And let me just write that down. I'm going to call this the y equals 1 region. And in contrast, the region where x1 plus x2 is less than 3, that's when we will predict that y is equal to 0, and that corresponds to this region. It's really a half plane, but that region on the left is the region where our hypothesis will predict y equals 0. I want to give this line, this magenta line that I drew a name. This line there is called the decision boundary. And concretely, this straight line, x1 plus x2 equals 3, that corresponds to the setter point, so that corresponds to the region where h of x is equal to 0.5 exactly. And the decision boundary, that is this straight line, that's the line that separates the region where the hypothesis predicts y equals 1 from the region where the hypothesis predicts that y is equal to 0. And just to be clear, the decision boundary is a property of the hypothesis, including the parameters theta 0, theta 1, theta 2. And in the figure, I drew a training set, I drew a data set in order to help the visualization. But even if we take away the data set, this decision boundary and the region where we predict y equals 1 versus y equals 0, that's a property of the hypothesis and of the parameters of the hypothesis, and not a property of the data set. Later on, of course, we'll talk about how to fit the parameters, and there we'll end up using the training set, using our data to determine the value of the parameters. But once we have particular values for the parameters theta 0, theta 1, theta 2, then that completely defines the decision boundary, and we don't actually need to plot a training set in order to plot the decision boundary. Let's now look at a more complex example where, as usual, I have crosses to denote my positive examples and O's to denote my negative examples. Given a training set like this, how can I get logistic regression to fit this sort of data? Earlier, when we were talking about polynomial regression, or when we were talking about linear regression, we talked about how we can add extra higher order polynomial terms to the features, and we can do the same for logistic regression. Concretely, let's say my hypothesis looks like this, where I've added two extra features, x1 squared and x2 squared, to my features, so that I now have 5 parameters, theta 0 through theta 4. As before, we'll defer to the next video, our discussion on how to automatically choose values for the parameters theta 0 through theta 4. But let's say that via procedure to be specified, I end up choosing theta 0 equals minus 1, theta 1 equals 0, theta 2 equals 0, theta 3 equals 1, and theta 4 equals 1. What this means is that with this particular choice of parameters, my parameter vector theta looks like minus 1, 0, 0, 1, 1. Following our earlier discussion, this means that my hypothesis will predict that y is equal to 1 whenever minus 1 plus x1 squared plus x2 squared is greater than or equal to 0. This is whenever theta transpose times my theta transpose my features is greater than or equal to 0. And if I take minus 1 and just bring this to the right, I'm saying that my hypothesis will predict that y is equal to 1 whenever x1 squared plus x2 squared is greater than or equal to 1. So what does this decision boundary look like? Well, if you were to plot the curve for x1 squared plus x2 squared equals 1, some of you will recognize that that is the equation for a circle of radius 1 centered around the origin. So that is my decision boundary. And everything outside the circle, I'm going to predict as y equals 1. So out here is my y equals 1 region. I'm going to predict y equals 1 out here. And inside the circle is where I'll predict y is equal to 0. So by adding these more complex or these polynomial terms to my features as well, I can get more complex decision boundaries that don't just try to separate the positive and negative examples of a straight line, but I can get, in this example, a decision boundary that's a circle. Once again, the decision boundary is a property not of the training set, but of the hypothesis and of the parameters. So long as we're given my parameter vector theta, that defines the decision boundary, which is the circle. But the training set is not what we use to define the decision boundary. The training set may be used to fit the parameters theta. We'll talk about how to do that later. But once you have the parameters theta, that is what defines the decision boundary. Let me put back the training set just for visualization. And finally, let's look at a more complex example. So can we come up with even more complex decision boundaries than this? If I have even higher order polynomial terms, so things like x1 squared, x1 squared, x2, x1 squared, x2 squared, and so on. If I have much higher order polynomials, then it's possible to show that you can get even more complex decision boundaries, and logistic regression can be used to find decision boundaries that may, for example, be an ellipse like that, or maybe with a different setting of the parameters. Maybe you can get instead a different decision boundary, which may even look like, some funny shape like that. Or for even more complex examples, maybe you can also get decision boundaries that could look like, more complex shapes like that, where everything in here you predict y equals 1, and everything outside you predict y equals 0. So these higher order polynomial features, you can get very complex decision boundaries. So with these visualizations, I hope that gives you a sense of what's the range of hypothesis functions we can represent using the representation that we have for logistic regression. Now that we know what h of x can represent, what I'd like to do next in the following video is talk about how to automatically choose the parameters theta so that given a training set, we can automatically fit the parameters to our data. In this video, we'll talk about how to fit the parameters theta for logistic regression. In particular, I'd like to define the optimization objective, or the cost function that we'll use to fit the parameters. Here's the supervised learning problem of fitting a logistic regression model. We have a training set of m training examples, and as usual, each of our examples is represented via a feature vector that's n plus 1 dimensional. And as usual, we have x0 equals 1, first feature, or 0 feature is always equal to 1. And because this is a classification problem, our training set has the property that every label y is either 0 or 1. This is our hypothesis, and the parameters of the hypothesis is this theta over here. And the question I want to talk about is, given this training set, how do we choose or how do we fit the parameters theta? Back when we were developing the linear regression model, we used the following cost function. I've written this slightly differently, where instead of 1 over 2m, I've taken the 1/2 and put it inside the summation instead.
So if you really want to get fit after 50, what's the first thing to do? Stop.
Now, I want to use an alternative way of writing out this cost function, which is that instead of writing out the squared error term here, let's write in here cost of h of x, comma y, and I'm going to define that term cost of h of x, comma y to be equal to this. It's just equal to this 1/2 of the squared error. So now we can see more clearly that the cost function is a sum over my training set, or is 1 over m times the sum over my training set of this cost term here. And to simplify this equation a little bit more, it's going to be convenient to get rid of those superscripts. So just define cost of h of x, comma y to be equal to 1/2 of this squared error. And the interpretation of this cost function is that this is the cost I want my learning algorithm to, have to pay if it outputs that value, if its prediction is h of x and the actual label was y. So let's just cross off those superscripts, right? And no surprise, for linear regression, the cost we've defined is that, well, the cost for this is that is 1/2 times the square difference between what it predicted and the actual value that we observed for y. Now, this cost function worked fine for linear regression, but here we're interested in logistic regression. If we could minimize this cost function that is plugged into J here, that would work okay. But it turns out that if we use this particular cost function, this would be a non-convex function of the parameters theta. Here's what I mean by non-convex. We have some cost function j of theta, and for logistic regression, this function h here has a nonlinearity, right? It says, 1 over 1 plus e to the negative theta transpose x. So this is a pretty complicated nonlinear function. And if you take this sigmoid function, plug it in here, and then take this cost function and plug it in there, and then plot what j of theta looks like, you find that j of theta can look like a function that's like this, with many local optima. And the formal term for this is that this is a non-convex function. And you can kind of tell, if you were to run gradient descent on this sort of function, it is not guaranteed to converge to the global minimum. Whereas in contrast, what we would like is to have a cost function j of theta that is convex, that is a single bow-shaped function that looks like this, so that if you run gradient descent, we would be guaranteed that gradient descent would converge to the global minimum. And the problem with using the squared cost function is that because of this very nonlinear sigmoid function that appears in the middle here, j of theta ends up being a non-convex function if you were to define it as the squared cost function. So what we'd like to do is to instead come up with a different cost function that is convex, and so that we can apply a great algorithm like gradient descent and be guaranteed to find the global minimum. Here's the cost function that we're going to use for logistic regression. We're going to say that the cost or the penalty that the algorithm pays if it outputs a value h of x, so if this is some number like 0.7, right? But if it predicts a value h of x and the actual clause label turns out to be y, the cost is going to be minus log h of x if y is equal to 1, and minus log 1 minus h of x if y is equal to 0. This looks like a pretty complicated function, but let's plot this function to gain some intuition about what it's doing. Let's start off with the case of y equals 1. If y is equal to 1, then the cost function is minus log h of x. And if we plot that, so let's say that the horizontal axis is h of x, so we know that our hypothesis is going to output a value between 0 and 1, right? So h of x varies between 0 and 1. If you plot what this cost function looks like, you find that it looks like this. One way to see why the plot looks like this is because if you were to plot log z with z on the horizontal axis, then that looks like that, and it sort of approaches minus infinity, right? So this is what the log function looks like. And this is 0, this is 1. Here, z is, of course, playing the role of h of x. And so minus log z will look like this, right? Just flipping the sign, minus log z. And we're interested only in the range of when this function goes between 0 and 1. So get rid of that. And so we're just left with, this part of the curve. And that's what this curve on the left looks like. Now, this cost function has a few interesting and desirable properties. First, you notice that if y is equal to 1 and h of x is equal to 1, in other words, if the hypothesis exactly predicts h equals 1 and y is exactly equal to what it predicted, then the cost is equal to 0, right? That corresponds to the curve doesn't actually flatten out. The curve is still going. First, notice that if h of x equals 1, if the hypothesis predicts that y is equal to 1, and if indeed y is equal to 1, then the cost is equal to 0. That corresponds to this point down here, right? If h of x is equal to 1, and we're only considering the case that y equals 1 here, but if h of x is equal to 1, then the cost is down here, is equal to 0, and that's what we'd like it to be, because if we correctly predict the output y, then the cost is 0. But now notice also that as h of x approaches 0, so as the output of a hypothesis approaches 0, the cost blows up and it goes to infinity. And what this does is this captures the intuition that if a hypothesis outputs 0, that's like saying a hypothesis saying the chance of y equals 1 is equal to 0. It's kind of like going to a medical patient and saying the probability that you have a malignant tumor, the probability that y equals 1, is 0. So it's like absolutely impossible that your tumor is malignant. But if it turns out that the patient's tumor actually is malignant, so if y is equal to 1, even after we told them, that the probability of it happening is 0. So it's absolutely impossible for it to be malignant. But if we told them this with that level of certainty and we turn out to be wrong, then we penalize the learning algorithm by a very, very large cost. And that's captured by having this cost go to infinity if y equals 1 and h of x approaches 0. This slide considered the case of y equals 1. Let's look at what the cost function looks like for y equals 0. If y is equal to 0, then the cost looks like this. It looks like this expression over here. And if you plot the function minus log 1 minus z, what you get is the cost function actually looks like this. So it goes from 0 to 1, kind of like that. And so if you plot the cost function for the case of y equals 0, you find that it looks like this. And what this curve does is it now blows up and goes to plus infinity as h of x goes to 1, because it's saying that if y turns out to be equal to 0, but we predicted that y is equal to 1 with almost certainty, with probably 1, then we end up paying a very large cost. Let's plot the cost function for the case of y equals 0. So if y equals 0, that's going to be our cost function. If you look at this expression and if you plot minus log 1 minus z, if you figure out what that looks like, you get a figure that looks like this, which goes from 0 to 1 with the z-axis on the horizontal axis. So if you take this cost function and plot it for the case of y equals 0, what you get is that the cost function looks like this. And what this cost function does is that it blows up, or it goes to a positive infinity as h of x goes to 1. And this captures the intuition that if a hypothesis predicted that h of x is equal to 1 with certainty, with like probably 1, it's absolutely got to be y equals 1. But if y turned out to be equal to 0, then it makes sense to make the hypothesis or make the learning algorithm pay a very large cost. And conversely, if h of x is equal to 0 and y equals 0, then the hypothesis nailed it. It predicted y is equal to 0, and it turns out y is equal to 0. So at this point, the cost function is going to be 0. In this video, we've defined the cost function for a single training example. The topic of convexity analysis is beyond the scope of this course, but it is possible to show that with our particular choice of cost function, this would give us a convex optimization problem. Says our overall cost function j of theta will be convex and local optima free. In the next video, we're going to take these ideas of the cost function for a single training example and develop that further and define the cost function for the entire training set. And we'll also figure out a simpler way to write it than we have been using so far. And based on that, we'll work out gradient descent, and that will give us our logistic regression algorithm. In this video, we'll figure out a slightly simpler way to write the cost function than we have been using so far. And we'll also figure out how to apply gradient descent to fit the parameters of logistic regression. So by the end of this video, you know how to implement a fully working version of logistic regression. Here's our cost function for logistic regression. Our overall cost function is 1 over m times sum over the training set of the cost of making different predictions on the different examples with labels yi. And this was the cost for a single example that we worked out earlier. And just want to remind you that for classification problems in our training set, and in fact, even for examples not in our training set, y is always equal to 0 or 1, right? That's sort of part of the mathematical definition of y. Because y is either 0 or 1, we'll be able to come up with a simpler way to write this cost function. And in particular, rather than writing out this cost function on 2 separate lines with 2 separate cases for y equals 1 and y equals 0, I'm going to show you a way to take these 2 lines and compress them into one equation. And this will make it more convenient to write out a cost function and derive gradient descent. Concretely, we can write out the cost function as follows. We'll say that cost of h of x comma y, I'm going to write this as minus y times log h of x minus 1 minus y times log 1 minus h of x. And I'll show you in a second that this expression or this equation is a equivalent way or more compact way of writing out this definition of the cost function that we had up here. Let's see why that's the case. We know that there are only two possible cases. Y must be 0 or y or 1. So let's suppose y equals 1. If y is equal to 1, then this equation is saying that the cost is equal to, well, if y is equal to 1, then this thing here is equal to 1, and 1 minus y is going to be equal to 0, right? So if y is equal to 1, then 1 minus y is 1 minus 1, which is therefore 0. So the second term gets multiplied by 0 and goes away, and we're left with only this first term, which is y times log minus y times log h of x. Y is 1, so that's equal to minus log h of x. And this equation is exactly what we have up here for if y is equal to 1. The other case is if y is equal to 0. And if that's the case, then our writing of the cost function is saying that, well, if y is equal to 0, then this term here would be equal to 0, whereas 1 minus y, if y is equal to 0, would be equal to 1, because 1 minus y becomes 1 minus 0, which is just equal to 1. And so the cost function simplifies to just this last term here, right? Because the first term over here gets multiplied by 0 and so disappears, so we're just left with this last term, which is minus log 1 minus h of x. And you can verify that this term here is just exactly what we had for when y is equal to 0. So this shows that this definition for the cost is just a more compact way of taking both of these expressions, the cases y equals 1 and y equals 0, and writing them in in a more convenient form with just one line. We can therefore write out our cost function for logistic regression as follows. It is this 1 over m of the sum of these cost functions, and plugging in the definition for the cost that we worked out earlier, we end up with this, and it just brought the minus sign outside. And why did we choose this particular function? Well, it looks like there could be other cost functions we could have chosen. Although I won't have time to go into great detail of this in this course, this cost function can be derived from statistics using the principle of maximum likelihood estimation, which is an idea in statistics for how to efficiently find parameters data for different models. And it also has a nice property that it is convex. So this is the cost function that, essentially everyone uses when fitting logistic regression models. If you don't understand the terms that I just said, sort of if you don't know what the principle of maximum likelihood estimation is, don't worry about it, but there's just a deeper rationale and justification behind this particular cost function than I have time to go into in this class. Given this cost function, in order to fit the parameters, what we're going to do then is try to find the parameters theta that minimize j of theta. So if we try to minimize this, this would give us some set of parameters theta. Finally, if we're given a new example with some set of features x, we can then take the thetas that we fit to our training set and output our prediction as this. And just to remind you, the output of my hypothesis I'm going to interpret as the probability that y is equal to 1. And this is given the input x and parameterized by theta. But just think of this as just my hypothesis is estimating the probability that y is equal to 1. So all that remains to be done is figure out how to actually minimize j of theta as a function of theta so that we can actually fit the parameters to our training set. The way we're going to minimize the cost function is using gradient descent. Here's our cost function, and if we want to minimize it as a function of theta, here's our usual template for gradient descent, where we repeatedly update each parameter by updating it as itself minus the learning rate alpha times this derivative term. If you know some calculus, feel free to take this term and try to compute the derivative yourself and see if you can simplify it to the same answer that I get. But even if you don't know calculus, don't worry about it. If you actually compute this, what you get is this equation, and I'll just write it out here, is sum from I equals 1 through m of essentially the error times xij. So if you take this partial derivative term and plug it back in here, we can then write out our gradient descent algorithm as follows. And all I've done is I took the derivative term from the previous slide and plugged it in there. So if you have n features, you would have, a parameter vector theta, which with parameters theta 0, theta 1, theta 2, down to theta n, and you would use this update to simultaneously update all of your values of theta. Now, if you take this update rule and compare it to what we were doing for linear regression, you might be surprised to realize that, well, this equation was exactly what we had for linear regression. In fact, if you look in the earlier videos and look at the update rule, the gradient descent rule for linear regression, it looked exactly like what I drew here inside the blue box. So are linear regression and logistic regression different algorithms or not? Well, this is resolved by observing that for logistic regression, what has changed is that the definition for this hypothesis has changed. So whereas for linear regression, we had h of x equals theta transpose x, now the definition of h of x has changed and is instead now 1 over 1 plus e to the negative theta transpose x. So even though the update rule looks cosmetically identical because the definition of the hypothesis has changed, this is actually not the same thing as gradient descent for linear regression. In an earlier video, when we were talking about gradient descent for linear regression, we had talked about how to monitor gradient descent to make sure that it is converging. I usually apply that same method to logistic regression too, to monitor gradient descent to make sure it's converging correctly, and hopefully you can figure out how to apply that technique to logistic regression yourself. When implementing logistic regression with gradient descent, we have all of these different parameter values, theta 0 down to theta n that we need to update using this expression. And one thing we could do is have a for loop. So for I equals 0 to n, or for I equals 1 to n plus 1, to update each of these parameter values in turn. But of course, rather than using a for loop, ideally we would also use a vectorized implementation. And so that a vectorized implementation can update, all of these n plus 1 parameters all in one fell swoop. And to check your own understanding, you might see if you can figure out how to do the vectorized implementation of this algorithm as well. So now you know how to implement gradient descent for logistic regression. There was one last idea that we had talked about earlier for linear regression, which was feature scaling. We saw how feature scaling can help gradient descent converge faster for linear regression. The idea of feature scaling also applies to gradient descent for logistic regression, and if you have features that are on very different scales, then applying feature scaling can also make gradient descent run faster for logistic regression. So that's it. You now know how to implement logistic regression, and this is a very powerful and probably the most widely used classification algorithm in the world, and you now know how to get to work for yourself. In the last video, we talked about gradient descent for minimizing the cost function j of theta for logistic regression. In this video, I'd like to tell you about some advanced optimization algorithms and some advanced optimization concepts. Using some of these ideas, we'll be able to get logistic regression to run much more quickly than is possible with gradient descent, and this will also let the algorithms scale much better to very large machine learning problems, such as if we have a very large number of features. Here's an alternative view of what gradient descent is doing. We have some cost function j, and we want to minimize it. So what we need to do is we need to write code that can take as input the parameters theta, and that can compute two things, j of theta and these partial derivative terms for j equals 0, 1 up to n. given code that can do these two things, what gradient descent does is it repeatedly performs the following update, right? So given the code that we wrote to compute these partial derivatives, gradient descent plugs us in here and uses that to update our parameters data. So another way of thinking about gradient descent is that we need to supply code to compute j of theta and these derivatives, and then these get plugged into gradient descent, which can then try to minimize the function for us. For gradient descent, I guess technically you don't actually need code to compute the cost function j of theta. You only need code to compute the derivative terms. But if you think of your code as also monitoring convergence or some such, we'll just think of ourselves as providing code to compute both the cost function and the derivative terms. So, having written code to compute these two things, one algorithm we can use is gradient descent. But gradient descent isn't the only algorithm we can use, and there are other algorithms, more advanced, more sophisticated ones, that if we only provide them a way to compute these two things, then these are different approaches to optimize the cost function for us. So conjugate gradient, BFGS, and LBFGS are examples of more sophisticated optimization algorithms that need a way to compute j of theta and need a way to compute the derivatives, and can then use more sophisticated strategies than gradient descent to minimize the cost function. The details of exactly what these three algorithms do is well beyond the scope of this course, and in fact, you often end up spending many days or a small number of weeks studying these algorithms if you take a class in advanced numerical computing. But let me just tell you about some of their properties. These three algorithms have a number of advantages. One is that with any of these algorithms, you usually do not need to manually pick the learning rate alpha. So one way to think of these algorithms is that given the way to compute the derivative and the cost function, you can think of these algorithms as having a clever inner loop. And in fact, they have a clever inner loop called a line search algorithm that automatically tries out different values for the learning rate alpha and automatically picks a good learning rate alpha, so that it can even pick a different learning rate for every iteration. And so then you don't need to choose it yourself. These algorithms actually do more sophisticated things than just pick a good learning rate, and so they often end up converging much faster than gradient descent. These algorithms actually do more sophisticated things than just pick a good learning rate, and so they often end up converging much faster than gradient descent, but a detailed discussion of exactly what they do is beyond the scope of this course. In fact, I actually used to have used these algorithms for a long time, like maybe over a decade, quite frequently. And it was only a few years ago that I actually figured out for myself the details of what conjugate gradient, BFGS, and LBFGS do. So it is actually entirely possible to use these algorithms successfully and apply to lots of different learning problems without actually understanding the inner loop of what these algorithms do. If these algorithms have a disadvantage, I'll say that the main disadvantage is that they're quite a lot more complex than gradient descent. And in particular, you probably should not implement these algorithms, conjugate gradient, LBFGS, BFGS, yourself, unless you're an expert in numerical computing. Instead, just as, I wouldn't recommend that you write your own code to compute square roots of numbers or to compute inverses of matrices. For these algorithms also, what I would recommend you do is just use a software library. So, to take a square root, what all of us do is use some function that someone else has written to compute the square roots of our numbers. And fortunately, Octave and the closely related language MATLAB, if you're using that, Octave has a very good, has a pretty reasonable library implementing some of these advanced optimization algorithms. And so if you just use the built-in library, you get pretty good results. I should say that there is a difference between good and bad implementations of these algorithms. And so if you're using a different language for your machine learning application, if you're using like C, C++, Java, and so on, you might want to try out a couple different libraries to make sure that you find a good library for implementing these algorithms, because there is a difference in performance between a good implementation of conjugate gradient or LBFGS versus a less good implementation of conjugate gradient or LBFGS. So now let's explain how to use these algorithms. I'm going to do so with an example. Let's say that you have a problem with two parameters, or theta equals theta 0 and theta 1. And let's say your cost function is j of theta equals theta 1 minus phi squared plus theta 2 minus phi squared. So with this cost function, the value for theta 1 and theta 2, if you want to minimize j of theta as a function of theta, the value that minimizes it is going to be theta 1 equals 5, theta 2 equals 5. Now, again, I know some of you know more calculus than others, but the derivatives of the cost function j turn out to be these two expressions down here, so I've done the calculus. So if you want to apply one of the advanced optimization algorithms to minimize this cost function j, so if we didn't know the minimum was at 5, but if you want to have a cost function, find the minimum numerically, right, using something like gradient descent, but preferably more advanced than gradient descent, what you would do is implement an octave function like this. So we implement a cost function theta function like that. And what this does is it returns two arguments. The first, jval, is how we would compute the cost function j. And so this says jval equals theta 1 minus phi squared plus theta 2 minus phi squared. So it's just computing this cost function over here. And the second argument that this function returns is gradient. So gradient is going to be a 2 by 1 vector, and the two elements of the gradient vector correspond to the two partial derivative terms over here. Having implemented this cost function, you can then call the advanced optimization function called fminunc. It stands for function minimization unconstrained in octave. And the way you call this is as follows. You set a few options. This is options is a data structure that stores the options you want. So grad op on, this sets the gradient objective parameter to on. It just means that you are indeed going to provide a gradient to this algorithm. And we're going to set the maximum number of iterations to, let's say, 100. We're going to give it an initial guess for theta. This is a 2 by 1 vector. And then this command calls fminunc. This @ symbol represents a pointer to the cost function that we just defined up there. And if you call this will compute, we'll use one of the more advanced optimization algorithms. And if you want, think of it as just like gradient descent, but automatically choosing the learning rate alpha for you, so you don't have to do so yourself. But it will then attempt to use these sort of advanced optimization algorithms like gradient descent on steroids to try to find the optimal value of theta for you. Let me actually show you what this looks like in octave. So I've written this cost function of theta function exactly as we had it on the previous slide. It computes jval, which is the cost function, and it computes the gradient with the two elements being the partial derivatives of the cost function with respect to the two parameters theta 1 and theta 2. Now let's switch to my octave window. I'm going to type in those commands that I had just now. So options equals optimset. This is the notation for setting my parameters or my options for my optimization algorithm. Grad option on, max iter 100, so that says 100 iterations, and I am going to provide the gradient to my algorithm. Let's say initial theta equals zeros 2 by 1, so that's my initial guess for theta. And now I have op theta function val exit flag equals fmin unconstrained, a pointer to the cost function, and provide my initial guess and the options, like so. And if I hit enter, this will run the optimization algorithm. And it returns pretty quickly. Oh, this funny formatting, that's because my line, my code wrapped around. But so this funny thing is just because my command line had wrapped around. But what this says is that it numerically ran this, think of it as gradient descent on steroids, and it found the optimal value for theta is theta 1 equals 5, theta 2 equals 5, exactly as we're hoping for. The function value at the optimum is essentially 10 to the minus 30, so that's essentially 0, which is also what we're hoping for. And the exit flag is 1. And this shows what the convergence status of this. And if you want, you can do help fminunc to read the documentation for how to interpret the exit flag. But the exit flag lets you verify whether or not this algorithm thinks it has converged. So that's how you run these algorithms in Octave. I should mention, by the way, that for the Octave implementation, this value of theta, your parameter vector theta, must be in RD for d greater than or equal to 2. So if theta is just a row number, so if it's not at least a two-dimensional vector or some higher than two-dimensional vector, this fmin unc may not work. So if in case you have a one-dimensional function that you need to optimize, you can look in the Octave documentation for fmin unc for additional details. So that's how we optimize our toy example of this sort of simple quadratic cost function. How do we apply this to logistic regression? In logistic regression, we have a parameter vector theta, and I'm going to use a mix of Octave notation and sort of math notation, but I hope this explanation will be clear. But our parameter vector theta comprises these parameters theta 0 through theta n, because Octave indexes vectors using indexing from 1. You know, theta 0 is actually written theta 1 in Octave, theta 1 is going to be written so theta 2 in Octave, and that's going to be written theta n plus 1, right? And that's because Octave indexes its vectors starting from an index of 1 instead of an index from 0. So what we need to do then is write a cost function that captures the cost function for logistic regression. Concretely, the cost function needs to return jval, which is jval, so you need some code to compute j of theta. And we also need to give it the gradient. So gradient 1 is going to be some code to compute the partial derivative with respect to theta 0, the next partial derivative with respect to theta 1, and so on. And once again, this is gradient 0, this is gradient 1, gradient 2, and so on, rather than gradient 0, gradient 1, because Octave indexes its vectors starting from 1 rather than from 0. But the main concept I hope you take away from this slide is that what you need to do is write a function that returns the cost function and returns the gradient. And so in order to apply this to logistic regression, or even to linear regression, if you want to use these optimization algorithms for linear regression, what you need to do is plug in the appropriate code to compute these things over here. So now you know how to use these advanced optimization algorithms. Because for these algorithms you're using a sophisticated optimization library, it makes the code just a little bit more opaque, and so just maybe a little bit harder to debug. But because these algorithms often run much faster than gradient descent, often, quite typically, whenever I have a large machine learning problem, I will use these algorithms instead of using gradient descent. And with these ideas, hopefully you'll be able to get logistic regression and also linear regression to work on much larger problems. So that's it for advanced optimization concepts. And in the next and final video on logistic regression, I want to tell you how to take the logistic regression algorithm that you already know about and make it work also on multi-class classification problems.
Welcome to Crimson Global Academy.
In this video, we'll talk about how to get logistic regression to work for multi-class classification problems. And in particular, I want to tell you about an algorithm called one versus all classification. What's a multi-class classification problem? Here are some examples. Let's say you want a learning algorithm to automatically put your email into different folders or to automatically tag your emails. So you might have different folders or different tags for work email, email from your friends, email from your family, and emails about your hobby. And so here we have a classification problem with 4 classes, which we might assign the numbers, the classes y equals 1, y equals 2, y equals 3, and y equals 4 to. And another example, for medical diagnosis, if a patient comes into your office with maybe a stuffy nose, the possible diagnoses could be that they're not ill, maybe that's y equals 1, or they have a cold, 2, or they have a flu. And third and final example, if you are using machine learning to classify the weather, maybe you want to decide if the weather is sunny, cloudy, rainy, or snow, or if it's going to be snow. And so in all of these examples, y can take on a small number of discrete values, maybe 1 to 3, 1 to 4, and so on, and these are multi-class classification problems. And by the way, it doesn't really matter whether we index this as 0, 1, 2, 3, or as 1, 2, 3, 4. I tend to index my classes starting from 1 rather than starting from 0, but either way works, and it really doesn't matter. Whereas previously, for a binary classification problem, our data sets look like this. For a multi-class classification problem, our data sets may look like this, where here I'm using 3 different symbols to represent our 3 classes. So the question is, given a data set with 3 classes, where, this is an example of one class, that's an example of a different class, and that's an example of yet a third class, how do we get a learning algorithm to work for the setting? We already know how to do binary classification. Using logistic regression, we know how to, maybe fit a straight line to separate the positive and negative classes. Using an idea called one versus all classification, we can then take this and make it work for multi-class classification as well. Here's how one versus all classification works, and this is also sometimes called one versus rest. Let's say we have a training set like that shown on the left, where we have 3 classes. So if y equals 1, we denote that with a triangle. If y equals 2, the square. And if y equals 3, then the cross. What we're going to do is take our training set and turn this into 3 separate binary classification problems, or turn this into 3 separate 2-class classification problems. So let's start with class 1, which is a triangle. We're going to essentially create a new sort of fake training set where classes 2 and 3 get assigned to the negative class and class 1 gets assigned to the positive class. We're going to create a new training set like that shown on the right, and we're going to fit a classifier which I'm going to call h subscript theta superscript 1 of x, where here the triangles are the positive examples and the circles are the negative examples. So think of the triangles being assigned the value of 1 and the circles the value of 0. And we're just going to train a standard logistic regression classifier, and maybe that will give us a decision boundary that looks like that. Okay? This superscript 1 here stands for class 1, so we're doing this for the triangles of the first class. Next, we do the same thing for class 2. We're going to take the squares and assign the squares as the positive class and assign everything else, the triangles and the crosses, as the negative class. And then we fit a second logistic regression classifier. We'll call this h of x superscript 2, where the superscript 2 denotes that we're now doing this, treating the square class as the positive class. And maybe we get the classifier like that. And finally, we do the same thing for the third class and fit a third classifier, h superscript 3 of x, and maybe this will give us a decision boundary or give us a classifier that separates the positive and negative examples like that. So to summarize, what we've done is we've fit 3 classifiers. So for I equals 1, 2, 3, we've fit a classifier h superscript I subscript theta of x that's trying to estimate what is the probability that y is equal to class I given x and parameterized by theta, right? So in the first instance, for this first one up here, this classifier was learning to recognize the triangles. So it's thinking of the triangles as a positive class. So h superscript 1 is essentially trying to estimate what is the probability that the y is equal to 1 given x and parameterized by theta. And similarly, this is treating, the square class as a positive class, and so it's trying to estimate the probability that y is equal to 2, and so on. So we now have 3 classifiers, each of which was trained to recognize one of the 3 classes. Just to summarize, what we've done is we want to train a logistic regression classifier, h superscript I of x for each class I to predict the probability that y is equal to I. Finally, to make a prediction, when we're given a new input x and we want to make a prediction, what we do is we just run all, let's say run all 3 of our classifiers on the input x, and we then pick the class I that maximizes the 3. So we just, basically pick the classifier, pick whichever one of the 3 classifiers is most confident or sort of most enthusiastically says that it thinks it has the right class. So whichever value of I gives us the highest probability, we then predict y to be that value. So that's it for multi-class classification and one versus all method. And with this little method, you can now take the logistic regression classifier and make it work on multi-class classification problems as well. By now, you've seen a couple different learning algorithms, linear.
Okay, guys, let me stop share. Okay, so here we finished the logistic regression. The next session that will be from 2 to 5, correct? As based on our schedule, just let me check. I believe 2 to 5. Yeah, 2 to 5. So we will meet at 2. We will start with the regularization and the support vector machine. Guys, if you have any question, you can ask. If you don't have, you can leave, and see you at 2. Thank you, everybody. Thank you, Louis. Thank you, Yahao, Yang, Shiva, Karen, Hankon. So guys, if you don't have anything, you can leave. I'll stop recording right here.